Hi everybody, today I'm gonna talk about a simple circuit theory problem. I'm gonna solve this, and here you can see input voltage, and here the output. This is a typical RLC question, okay? And these are the R 5 kilo ohms and F 0.5 Henry, okay? And 250 nanofarads. Okay, nano means 10 to the minus 9, right? And in that question it is stated that input voltage 70 volt, and this means that this is in the step input waveform, okay? And V output is required to be derived, and since this is step input, or 70 times step input, and since this is a linear circuit, let's just ignore 70 for now, and if we derive V out, we are going to multiply it with 70 in the end, in the last step, okay? And let's just focus. Input voltage is step function, okay? So for that, let's derive the output over input transfer function, okay? This is like, u, g, y. Let's try to find y of s over g of s equals, no, y of s over u of s equals g of s, okay? Let's try to find this g of s term here, and in that analogy, u is input voltage and y is output voltage. Alright, let's do it all this, right? Alright, and here the first step that I said it is finding this transfer function, okay? And then since this is a step input, okay, y of s equals g of s times 1 over s, because step function, okay? And then find this term, and then find the inverse Laplace transform. Okay, this is basic algebra problem at this point. So first step is to find finding the transfer function, and here we can see there is a parallel connection here, and let's call it x, okay? X, and x, what is x? X is given by this term, and here this symbol indicates that L and C are connected in parallel connection. And let me write this recurve R1 parallel R2 R equivalent, right? R equivalent equals R1 times R2 over R1 plus R2. Okay, this is like, okay, we know it by heart at this point, and just multiply the terms and then sum them over, okay? And this is the expression we get. This is the x expression, and then let me get this curve here we can see, okay, x over r plus x. Okay, this is a basic, right? Let me kind of remind you that V in and V out, right? R1, R2. In that case, V out would be like R2 over R1 plus R2 times V in, right? Okay. This is a voltage divider, right? Voltage divider. Okay. Since that makes sense, I mean, and then here, this is the transfer function, and let's substitute x. Let's substitute x. This is the transfer function, and this is the x term, right? And here we substitute x, okay, and then let me get this, okay, we arrange the terms, we find this SF over S squared RLC plus SF plus R, okay, and then at this point let's substitute R, okay, 5000, and F 0.5, and C 250 nanofarad, means 250 10 to the minus 9, right? And here we see RLC. RLC is 625 times 10 to the minus 6, right? And this, okay, this is that term, all right, and this is F, all right, this is R. Here I'm writing this, and I'm writing this, okay, and then since we are going to supply step function, right, as an input, and we want to find the output, let's multiply it with 1 over s term, okay. This is the transfer function. Here I'll just copy it from here, right, and this is the step function, okay, and s terms cancel each other out, right? And then at this point, since we want to, you know, find the inverse Laplace transform of this term, and let's find the roots, okay, this is the roots, all right, and let's write this in this manner, okay, in this form, and then let's, what do we call it, partial function expansion, right? Partial fraction expansion. Here, to find the a term in the numerator, right, just copy the whole rational term, and then ignore the denominator term that corresponds to a, right, and then substitute the root, okay, just substitute it here like this, okay. I mean, this is like a, you know, easy way of doing this. The other way is just you know, substituting and solving for a and b, right? And after this substitution, a is given by this term and b is given by this term, right? Okay, here, okay, let's record what this is. This is v out, and we want to in s domain, by the way, and we want to find v out in time domain, right? And we are going to take the inverse Laplace transform of this term, and here let's remind ourselves that this is the, you know, the basic inverse Laplace transform equality, right? Here let's consider as constant, okay, this is just constant, right? Okay, and this is the what is this? This is the pole, or this is, let's call it root, right? Root, okay. Here a is root and e to the root times t, right? You can think of it that way if that makes you enough. Okay, record that better. Here this corresponds to this term, right? And the same logic applies here too. Okay, this is the coefficient, right? This is the constant, okay, coefficient of that term, and here this is the root, and here again the exponential term over the root, right? And let's arrange. I mean, to me at this point, by the way, I made a big mistake. Okay, let me change that. T and T and T and T. Okay, because we just, you know, transform the term from S domain to T domain, right? T domain, right? Because it's inverse Laplace. And here I forget the T, and after that I didn't forget T, I guess. Okay, this is T terms. All right, and let's arrange the terms a little. Yeah, I was going to say this. At this point, to me, it's like, okay, the problem is solved, but it is usually the case where they want you to, you know, arrange the terms and get rid of this imaginary terms. Okay, so since exp in exp of minus 400t plus 2800 jt, right? Let's like this: e to the a plus b t equals e to the a t plus e to the bt, right? Let's like this. Okay, factor out. Okay, just factored these terms. Okay, and again for that term as well, let's factor them, right? Let's factor it. By factoring we get these two expressions, and let's arrange them a little bit more, right? And notice this is like 5600 times 2, right? 5600 times 2. Okay, and since there is j, 5600 times 2j, right? Okay, and here this term and this term. Okay, we just arrange the terms, right? Okay, here x minus 400t terms also common, and then this is the term in parentheses, and this is at this point what we need to record, right? Here sine omega t, and at this point we can see that omega is 2800, right? And we just okay, substitute this term using this, you know, identity. This is like specialized form of Euler identity. Okay, here we get this term, and yeah, this is the last step. And since we just only split step, meaning we just only split 1 volt, this is t equals 0, right? We just only split this, but we needed to supply 70 volt, right? We need to supply this, and I'm just going to multiply it with 70. Okay, all other terms are same, right? And this is the answer. Okay, and thanks for watching.